power. Okay, thank you.
Thank you very much. Good morning. This very big pleasure for me to be chairman of this session of a hyper-complex seminar devoted to memoriam of Professor Ławrynowicz. And the first talk today is the talk of Professor Zhidong Zhang, exact solution of ferromagnetic three-dimensional Ising model and computational complexity of spin glass three-dimensional Ising system. Professor Zhang, please go ahead.
Okay. Hello, everyone. Good morning. First of all, I would like to thank you, the organizer of the conference, to invite me to give the talk. The title of my talk is Exact Solution of Ferromagnetic Three-Dimensional Ising Model and the Computational Complexity of the Spin Glass 3D Ising System. I'm Zhidong Zhang from the Institute of Metal Research, Chinese Academy of Science. My talk have two parts. The first part is the exact solution. In the nature, it's they always have two different phases, the order and the disorder phase. The order means ordering no symmetry. The disorder means random chaotic high symmetry. Between the two phases, there are a critical point in which there's a very interesting critical phenomenon. The phases are very interesting in studying the critical phenomenon at the critical point. The critical phenomenon is very natural and universal in nature system. For instance, in the water, we have a phase diagram of the solid, liquid, and gas phase diagram. So you can see with changing the pressure and the temperature, we can have the bordering between the two different phases. There are a critical point in which we have two phases coexist. It means at this critical point, we don't know the phase is liquid or gas. So this phase diagram is very universal for many different materials. In all magnetic materials, there are also ordering phase. For instance, at the low temperature, we have the ferromagnetism, which is an order phase due to the local exchange interaction between spin. You can see all the spin are analyzed parallelly at the low temperature. At the high temperature, we have a disorder phase, which is called ferromagnetism, which is due to the temperature, we can have the spin aligned disorderly. One of the simple model to describe the critical phenomenon is the Ising model. In 1925, Ising solved exactly the 1D Ising model. In the Ising model, we have n spin located at the site of 1D, 2D, or 3D lattice. Each spin have two possible states or value is equal to +1, -1. So this is Hamiltonian of the system. The first term is the interact energy between the spin. The second term is due to the magnetic field. It's called the Neumann energy term. We can consider the interaction J between only the nearest neighboring spins. Here is the professor's answer. He solved exactly a two-dimensional Ising model in 1944. Then his student, Miss Kaufman, in 1949, developed a simple and angular spinor analysis for 2D Ising model. Her method simpler than Ansker's method, so we can follow it. So I just introduced briefly the Ansgar-Kaufman process. In the solid state physics, we can use the Pareto bordering condition for 3 directions to calculate the energy band. But here, because the Ising model is a many-body interaction problem, we can only use 1 times the Pareto bordering condition. Then the 1D problem is reduced to deal with the angle value of 2 plus 2 transform matches. So it's very simple. But for the 2-dimensional system, it's very complicated. We need to deal with the 2 transform matches with much larger size. The size is 2 power n times 2 power n. First, these 2 transform matches are represented as direct product of Pauli matches and their linear combination to be as a spin representation of the 2 matches. Second, the angle value of the 2 transform matches in spin representation are proved to be equal to those of the corresponding rotation matches with size 2n times 2n, which are in a special form to be dealt with easily. Finally, we can derive the potential function and free energy and also another thermodynamic physics problem of the system. However, what is the exact solution of 3D Ising model, which are very difficult, is a long-standing hard problem in physics. In 2007, I proposed 2 conjectures on exact solution of 3D Ising model. The paper was published in Philosophy magazine. So what I proposed is we first to study the transform matches in colorful algebra representation. There are total 3 transform matches, V1, V2, and V3. The first 2 transform matches are similar to 2-dimensional Ising model, which are in linear form in 2 gamma matches product. So these are very easy to deal with if we follow the Ansgar-Kaufman's process. But the V3 is a new transform matrix, which is for the 3rd dimension. So you can see here some gamma matrix, which is non-linear terms. We call it the W factor is internal factor. This factor is for every size of Ising spin. So it's make a very complicated problem. The gamma matrix is defined as direct product of Pauli matrix. The C and S are Pauli matrix with the unit matrix. So we deal with the colorful algebra in this way. The gamma matrix follows the anti-commutativity condition. If we interchange the position of gamma matrix, we opt the additional negative sign. So let's make a trouble for exact solution because it always generalizes the negative size. So the internal factor W are the key problem for 3D Ising model, which is topologically low trivial. So it means in the 3D Ising model, we have the topological problem. How to deal with it? I propose 2 conjectures. The first conjunction is the topological problem of 3D Ising model can be solved by introduce additional rotation in a 4-dimensional space. Since according to topological series, the knots in a 3D space can be opened by a rotation in 4D space. It comes from the topological series. So we can apply this to the 3D Ising model to find a spin representation in very high space for this additional rotation. Then, meanwhile, the 3 transform matrix V1, V2, V3 has to be rearranged also in the high space. My second conjunction is these 3 weight effects are generalized on the angle vector, which represent the contribution of energy in the 4D space to the energy spectrum of 3D system. This representing a projection from 4D to 3D. Then we can follow the Ansgar-Kaufman procedure in 3D dimension to solve exactly the 2D Ising model. This is my idea, but to confirm the correctness, we need to perform the 2 conjugation. After the publication of my paper, the paper received some comments from some statistical physicists. They are all very famous person in the physics. They have published many papers to give the comments. Due to the time limit, I cannot introduce in detail what they're talking about in the content. But I just wanted to appreciate Professor Junior Nowosky and co-workers. They published several papers to support my results. They introduced Clifford algebra, commutativity, and Yorkton algebra. Also discussed quaternion sequence of Yorkton algebra and talk about the base of the quantum mechanism within Yorkton von Neumann-Wigner procedure. It's a very important idea for me. And before I actually do not know the Yorkton algebra. So this paper great support to me and encourage me to carry out my progress further. So they are publishing more papers, and so it's important the Yorkton algebra. This formula is Yorkton algebra. So in this formula, we can deal with the anti-commutativity of the gamma matrix. As I mentioned before, the gamma matrix is anti-commutativity. But if we use the Yorkton algebra, then we can solve the problem to overcome the difficulty for interchanging the gamma matrix. This paper is a very important paper of Yorkton von Neumann and Wigner papers. They give the mathematical basis of quantum mechanism. So in 2012, Junior invited me to visit Poland. I very pleased to attend the hyper-complex seminar. So I'm enjoying my time in Poland. It's a very good memory of me. So you can see Professor Suzuki also here.
Yeah.
Yes.
I was young.
So in 2013, I invited Junior and Agnieszka Margaritska to visit Shenyang. We attended this symposium on binary ternary clinical analysis in Shenyang. Then in September 2013, Professor Suzuki also visited Shenyang. Yes, you are very young. So starting from this time, we have the cooperation, try to prove my conjectures. I think Professor Suzuki are a very important person in my life. So you help me to continue.
For me also.
So I visited Poland in 2015. So this is my second time visit. So in 2019, in cooperation with Professor Suzuki and Professor March of Oxford University. So we published this paper for the clinical algebra approach of 3D Ising model. So this paper, we discussing the nonlinear problem in the internet fact. In the transform method, I say that the V3 are very complicated. You can see here is Sj plus n. In our model, we only consign the nearest neighboring interaction between spin. But in this transform matrix, you can see this spin is not like non-range interaction. So it means along the third dimension, we have the non-range interaction effectively. We can have the formula. You see, for every spin, you can have the non-range interaction. So we try to start this system by using the trace, the property of the matrix, the trace of the matrix, the direct product. If we edit additional unit matrix, we generalize a factor of 2 for the trace. So if we edit k terms of the unit matrix, we generate the 2 power k fact. It means if we compensate this fact, we can keep the trace unchanged. It means the partition function and the physical properties are unchanged. And we can see if we interchange the position of the matrix in the trace, we have the same trace. So our series is that. The first series is the trace invariance series. The partition function of 3D Ising model is changed a factor of 2 power k by additing k terms of unit matrix in the direct product of the original transform matrix. This factor 2k can be compensated by division to keep the invariance of the trace. And again, and additionally, adjusting the sequence of the unit matrix with another matrix separate the exponential facts for different rows. So in the transform matrix, the exponential facts for each rows are isolated by the unit matrix, so there can be treated in sub-matches of transform matches to be dealt with it separately. So you can see there's a formula. We can separate the original matches with many unit matches. So we can separate the system. It means we first expand the 3D system to be 3 plus 1 dimension. Then we separate all the planes to be quasi 2D system. There are many sub-systems. Then we prove the larger 3 series. Due to the time limit, I cannot introduce in detail how we prove it. We prove the second one is the linearized series. A linearized process can be performed on the sub-transform matrix of 3D Ising model for each row. And while we splitting the system, the space. And the third one is a local transformation can be performed on the sub-transform matrix for each row. The local transform matrix changes the stage of the local system and trivializes the low trivialized topological structure, while it generalizes topological phase on the angle vector of 3D Ising model. The fourth series is the commutative series. The no commutative behavior of the operator in the linearization and the local transformation process of 3D Ising model can be dealt with to be commutative in framework of Yorkton von Neumann Wigner procedure with Yorkton algebra by perform time average of system of 3D Ising model. So I appreciate the Professor Yulia Nowatsky for his contribution. And in my paper, in our paper, in the acknowledgement, we appreciate his help for discussing. And then in this year, in cooperation with Professor Suzuki, we solve the problem using another method. This method is so-called Riemann-Hilbert problem. So the first step is a representation for the nodes space to the Clifford algebra of exponential types is constructed for partition function of 3D Ising model. After realizing the nodes on a Riemann surface and the monodromy representation is realized for the representation. Then we apply the Riemann-Hilbert problem and also the monoid transformation for the solution. So in this way, we trivialize the nodes in the high space, which is just my idea, my conjecture one. Then we introduce vortex operator of node type and a flat vertical bond, and renormalize the model by using of Gauss bonded chain formula. This is just my idea for the topological phase generalized in the angle vectors. So it's perform my conjunction 2. So the 2 paper will be published in mathematics. First paper is for conjunction 1. The second paper is for conjunction 2. And this, I just show briefly how we do it. First, we construct the node structure for the model. Then we realize it and using the monoid transformation. Then we open the low trivial topological structure to be trivial. And we construct the vortex operator Here is the mapping. Here's a mapping between the nodes and the spin lattice. You can see we have the two crossover on and up. So it's mapping to spin up and spin down with values +1 and -1. So here we have 2D nodes dimension. We can use this mapping to be two-dimensional Ising model.